You can download the biggest OpenAI model tonight. It's free, it's legal, and nobody stops you. 405 billion moving parts. Then you're stuck. Nothing you own can hold it. A model that size needs a building, which is why the companies running them keep theirs in warehouses and rent you a slot by the month. So people started building the warehouse at home. 2 NVIDIA boxes on a desk, 1 cable between them, and their own router on the front door instead of the one the internet company sent them. Can a desk really hold a 405 billion model? The strangest thing about this industry is that massive frontier models are just sitting on the open internet, waiting for you to click download. The only real constraint is finding a physical machine to put them on. And a growing subculture of developers decided they were tired of paying server rent. When you look at the real-world benchmarks people are casually posting, you'll see them treating a DGX Spark like a standard household appliance. And they aren't writing custom kernel scripts to do it, because they're just using standard off-the-shelf Ollama to load up the weights. Then they pipe the whole thing out securely through Tailscale, so they can talk to their own personal supercomputer from a coffee shop without exposing their home network to every wandering crypto bot. Which means the software side of this is basically a solved problem, and a model of this class is completely yours for the taking. So if the model is free and people are already running it in their spare bedrooms, what exactly is the machine that actually holds it? The machine NVIDIA actually built to pull this off is the DGX Spark, which is a surprisingly compact little box built around a single GB10 superchip that gives you 128 gigabytes of unified memory. That unified part is the core mechanical advantage, because instead of your processor and your graphics card fighting over a tiny data bridge like angry toddlers, they share the exact same pool of memory. And that means loading those massive weights suddenly isn't a bottleneck anymore, while the software side has matured so aggressively that the machine's actual performance has moved quite a bit since launch, without you having to buy new hardware. But if you want to put one of these in your spare bedroom, you're taking on a fairly heavy financial lift for a home lab, because the machine originally launched at $3,999. And then, in early 2026, NVIDIA apparently realized they were leaving money on the table, so they just casually hiked the list price mid-cycle, bringing it up to $4,699 today. So you're looking at nearly $5,000 for a machine that sits on your desk, and the obvious question is what exactly that price is actually buying, especially when you consider the entire box is mostly just 1 chip. The short answer is that you aren't really buying a proprietary machine at all, because that exact same GB10 Grace Blackwell superchip is already shipping inside rival compact boxes like the Asus Ascent GX10. You're actually just buying into a category of hardware, where NVIDIA provides the silicon and anyone else can handle the plastic shell. So while you might spend hours agonizing over which brand gives you the quieter cooling fan or a sleeker logo on the casing, the actual GB10 chip doing the inference math is identical across the board. What varies between these models is just the external packaging, the ports, and maybe how much of a markup you're willing to swallow for a green badge on the lid. Which means this whole tier of desktop AI hardware is essentially a commodity market now. But whichever vendor you end up handing your cash to, the hardware is limited to 128 gigs of memory, and trying to cram a 405 billion parameter model into that bucket is roughly like trying to park a commercial dump truck inside a studio apartment. The math just straight up refuses to work. If the absolute best machine in this compact class physically lacks the capacity to hold the model that everybody claims to be running locally, then how is anyone actually getting there? The answer is that you don't do it with one machine, because the people running these massive models at home are actually buying 2 DGX Spark units and wiring them together into a cluster. And instead of setting up a complex networking stack with an expensive enterprise switch that would draw even more power, you just link the 2 boxes directly using a single QSFP56 passive cable. Once they're physically connected over that direct 200 gigabit link, the architecture stops treating them as separate computers and instead pools their memory together. That pooled capacity is the exact hardware threshold you need to load a 405B parameter class model entirely into local memory without it spilling over and crashing your system. Which means, mechanically, the core promise is entirely true, and you really can fit the model into local memory across 2 desktop machines. But physically cramming the weights into the hardware so that they technically fit and actually living with this thing day to day are 2 very different tests. Because the reality is that once you solve the memory bottleneck, you immediately hit a whole new class of problems. So the obvious next question is, what a setup like this is actually good for once you finally turn it on. And if you look at the people who bought the hardware to solve those problems, they can't seem to agree on a single verdict. One enterprise review managed to call this setup overpromised, overpriced, and quietly indispensable, all in the exact same breath. Which sounds like a contradiction until you realize the machine is optimized for capacity over speed, built to hold massive models that need to fit and stay put. The internal bottlenecks mean the compute is weaker than the marketing implies. So if you fire this up expecting it to churn through thousands of tokens a second like a rented data center rack, you're going to be thoroughly disappointed. But you might just need a massive local sandbox for a model that normally requires a server room to even load into memory. And if you accept that it runs a little slow, the machine serves a very narrow, very real use case that matters for local development. Which means the hardware itself is basically a passive vessel, and the entire value of the setup is decided by the payload you put on it. So if the payload decides everything, what changes once your own daily work is the thing running on it? Because the moment you bring a massive AI model home, you're also dragging every proprietary codebase and half-baked idea you feed it directly into your own house. And since you probably still want to use it while you're sitting in a coffee shop, you end up doing exactly what people are already benchmarking, which is running Ollama and throwing Tailscale on the machine so you can reach it remotely. Which means the cheap plastic box your internet provider gave you for free is suddenly the entire perimeter standing between your unencrypted daily work and the open web. Because a router is really just a tiny computer running a strict set of rules, and its entire job is making sure the inside and the outside are kept genuinely separate. The hardware the door actually needs is small and cheap beside the compute half of the stack, but the one mandatory rule is that it has 2 network interfaces to enforce a hard physical divide. So if you're trusting a $4,699 piece of silicon with your data, and the default box in front of it is essentially a screen door on a submarine, what do you actually put on the front door instead? Well, for most people building an actual perimeter, the answer is OPNsense. It's a completely free, open source firewall platform built to run locally on your own equipment. People started migrating to it when a rival vendor shifted features behind a paid tier, which turns out to be a fantastic way to convince a bunch of paranoid homelabbers to pack up their networks and leave. And unlike the $4,699 superchip crunching the models, the hardware guarding the door is beautifully cheap and mundane. You don't need a water-cooled behemoth, you just need a standard low-power processor and 2 network interfaces so you can physically isolate your local data from the open internet. So instead of relying on a black box that might change its rules tomorrow, you basically just grab an ordinary little mini PC, flash the routing software, and suddenly you're the sole, absolute dictator of what gets to talk to your AI. It actually delivers on the promise, because pulling the supplied gateway out of the loop gets you off the vendor's upgrade cycle entirely and hands you a front door that you unequivocally own. You get to write the rules, you inspect the traffic, and you never have to worry about a mandatory firmware update suddenly breaking your local setup. But if the whole reason you went to all this trouble is to pull your data out of the cloud and establish absolute trust, you eventually have to ask what that trust is actually resting on. Swapping in OPNsense really just comes down to who you'd rather depend on. Vendor-managed platforms give you someone to blame when things break, and in exchange, they get to dictate exactly what features you're allowed to use. But when you go with fully open platforms like OpenWRT, They hand you complete control over your own network, which also means they hand you all the maintenance with it. Congratulations on your new part-time job, and say goodbye to the weekend you'll inevitably lose trying to configure it. You trade away a corporate support team for the transparency of open source software, mostly because you trust a loose coalition of paranoid developers to watch the code closer than a single company ever could. That trade gets you absolute authority over your own routing, meaning you're definitely freer without a vendor in the way, though you might not actually be any safer. Since you're the only one holding the keys to the perimeter, you're also the only one responsible for keeping the locks updated. So what happens when the open door you chose turns out to have a hole in it? Well, the answer to that arrived forcefully when the maintainers pushed out version 26.1.8 to patch 2 remote code execution vulnerabilities on the exact same day. With the first one, CVE 2026-44194, an attacker who already had an account with rights to manage users could turn that limited access into complete root control of the box just by feeding it a specifically crafted username, which meant it was basically the network equivalent of handing someone a key to the supply closet and watching them use it to instantly take ownership of the entire building. And since bad news usually travels in packs, the second bug patched in that release, CVE 2026-45158, opened up a completely separate route to running code on the router that came in through the network configuration side rather than the login. This one also couldn't just be triggered from the outside by a stranger, because it actually required an attacker who was already authenticated with high privileges to manipulate a DHCP hostname. So you had several serious flaws surfacing inside a single week, and the stakes here changed the second you move the model into your house, because a hole in the single piece of routing software guarding your perimeter directly exposes the private network where all the work you feed it actually lives. When you're the one holding the keys, a remote code execution vulnerability means somebody out there theoretically has a skeleton key of their own, which forces you to figure out how much control a flaw like that actually hands over. If you're looking at those remote execution flaws and assuming that an attacker still has to actively break in to run their code, you'd be missing a completely different class of problem hiding in the exact same software. Because it turns out you don't even need to breach the perimeter if you can just trick the guy holding the keys into opening the door from the inside. The National Vulnerability Database recorded CVE 2026-30868 as a flaw that allowed state-changing requests against the firewall's interface, which is a very sanitized way of describing a cross-site request forgery. Basically, if you were already logged into your router like a responsible admin, and you accidentally clicked a malicious link somewhere else, your browser would just quietly fire a command back at your firewall on the attacker's behalf. The attacker never learns your password, and they don't have to brute force a thing, because they're just wearing your active session like a cheap suit to alter the system state themselves. It represents a genuinely different kind of failure from the earlier bugs. The previous flaws had a stranger running code on the machine directly, while this one turns you into an unwitting weapon against your own network. And if someone can manipulate the router guarding your expensive local models just by waiting for you to browse the web with an active admin tab open, it leaves you wondering where the scale of severity actually tops out here. Well, from what the official vulnerability database shows, it tops out at a 9.1 out of 10, which lands it squarely in the critical tier. And that rating is just the public record, because a flaw like CVE 2026-44194 earns its score for a very mechanical reason. What this exploit actually handed out was remote code execution at the root level, but instead of letting a stranger run arbitrary commands, it allowed an attacker who already held a limited account with user management rights to seize the absolute highest privileges available on the machine. The problem here is that root is the absolute top of the permission stack, so there are zero restrictions above it to stop that rogue user from changing your network rules or just locking you out of your own hardware for fun. The gap between a legitimate restricted account and total ownership of the software guarding your house turned out to be exactly one crafted input wide, giving them a direct and completely unmonitored line to that expensive local AI setup sitting on your desk. So you have already spent the $4,699 to bring your models home, and you have taken on the maintenance of an open firewall to keep your prompts private, which makes you the sole security administrator for your own data. And when the front door you built can fail this badly from the inside, it really makes you look at the sheer amount of constant vigilance required to run a model safely and ask if holding your own keys is actually a trade you want to make. And that's before you even look at the authentication lockout bypass, which allowed a script to sit there brute forcing your login forever without the system ever actually shutting the door, at least until it was fixed in version 26.1.7 under CVE 2026-44195. Every single one of these vulnerabilities was disclosed out in the open and patched in a public release, which is exactly why people trust an open platform like OPNsense to begin with. A transparent fix only actually protects the owner who logs in and applies it, because nobody is pushing that security update down to your machine for you. So, can a desk really hold a $405 billion model? Well, the answer is mechanically yes, because the weights fit on the machine, the memory pools correctly over the cable, and you can absolutely get a model of this size running inside your own house without paying a monthly subscription. But when you pack up the capabilities of a cloud data center and drag them into your living room, what the desk doesn't replace is the team of network admins and security engineers that the warehouse came with. Owning the fast chip means you are also taking on the permanent maintenance of everything that touches the outside internet, and becoming the sole person responsible for whether the front door is actually locked. Anyways, that's all folks.